Hello, this time we'll talk about the Hausdorff dimension of the product of two Cantor sets. So let's start with the Cantor set. So assume that C is the Cantor set. Let me show you again the construction. So we have the unit interval, we call this E0. Then we take the left and right thirds. So from 0 to 1/3 and from 2/3 to 1. And then of the intervals we have, we take left and right thirds again, and we do this infinitely often. So we take C just to be the intersection of these of these EKs, which are so of course EK is a subset of EK minus 1. Okay, and we've already seen in a previous video that the Hausdorff dimension of the Cantor set is equal to log 2 over log 3. And now what we want to see now is what's the dimension of the product of two Cantor sets. So what's that? Okay, and first let me give you a note of caution. So in general, it's not true that the dimension of the product is equal to the sum of the dimensions. So you might expect something like that from linear algebra, but that's not true. So, but there are some conditions under which it is true. So, for instance, there are general inequalities. So some of these involve just the Hausdorff dimensions. Some of these inequalities involve the Hausdorff and the Minkowski dimensions, and so you can give some conditions when this is true. So let's say for F1 and F2, well, let's say for F1 in Rm and F2 in Rn, and let's say Borel, so that we can get that they are measurable with respect to the Hausdorff measure. Okay, so that's that, but now let's go back to our initial problem. So what's the dimension of this set, so of the product of two Cantor sets? And I claim that in this case we don't have any pathology, so this equality, which I said is in general not true, in this case it's actually true. So claim that this is just 2 times the dimension of the Cantor set, so which would be log 4 over log 3. Okay, now let's see what do we do now. So let me first give you another claim. Namely, I claim that the product of these two Cantor sets is just the intersection of these sets EK cross EK. So how do we see that? Well, let's first write down the definition. So this would be these intersections, and then here just the same again, and then we can write it as EL and then cross this, and this is certainly a subset of EL, so this whole thing would be a subset of this ek cross ek, so that's one direction, and the other direction we can also do this. So let's see. Let's say we have an element in, let's say we have x, y in this thing here. So we get that x is an ek for all k, and y is an ek for ek for all k, and so we get also that x is in this intersection here, and y is in this intersection. So these sets are equal, and it's a little bit more convenient to work with this because we have squares here. So these ek are rather union of squares. So E0 cross E0 would be a square, and then we have, let me show you. So let's maybe call this set ek prime. So these are now our new sets which we from which we construct the product of two Cantor sets. So that would be E0 prime. Then we would have here 4 squares, and then it would get smaller and smaller. So this would be E2 prime. So of course there are some more. So here for all squares we get 4 squares, and then we can go on like this. Okay, so let's see. Now we just will prove an upper bound, and we'll prove the lower bound probably in another video. So for the upper bound, this is quite convenient now, because we now look at the definition of the Hausdorff measure, and now we consider the covering. So we want to have a covering of the product of the two Cantor sets. So, and which covering do we take? Well, we just take the squares we have here. So how many squares do we have? Well, 4 to the k, and they have side length 3 to the minus k, and the diameter of one such square would be square root of 2 times 3 to the minus k. Okay, and now what do we have to look at? We have to look at so we have this sum over the, so we had this h as delta of let's say for some general set f. So then we had the infimum over such sums where ui was a delta cover of f. And so as it's the infimum, we just take such delta covering, and we take as delta covering the squares. And now let's see. So we have that this h as delta of f is at most, let me write it down. So h, s, and s delta we have, so we have to deal with the diameter, so that would be square root of 2, 3 to the minus k. Then this, and this would be at most, so we have 4 to the k, 4 to the k squares, and the diameter. And we want to look at the value of s, which would be, so which we hope to be the Hausdorff dimension, and we said that this should be the Hausdorff dimension. So let's look at it. So let's set s to be log 4 over log 3, and then we have log 4 over log 3. Okay, then we see that, well, this sum doesn't even depend on I, so we can make several things. So we get 4 to the k summand, then we have square root of 2 to the log 4 over log 3, then 3 to the minus k to the log 4 over log 3 is just 4 to the minus k, so we get square root of 2 log 4 over log 3, which is finite. So let's see, now we have that this is that this is bounded by this, so we get, now we take the limit for delta to 0 or k to infinity, so we get that hs of c cross c is at most this thing here, which is again finite. So we get, now let's see again at let's have a look at the Hausdorff dimension. So we have some part where the Hausdorff measure is infinite, then somewhere it can be finite, could also still be infinite, or could be 0, and then afterwards it's 0. And here we have that it's finite, so it has to be on this 0 line, which means that the Hausdorff dimension of f, so it has to be somewhere on this line, and so we have some point on this line here, so the Hausdorff dimension is at most log 4 over log 3. And we'll prove the other inequality in the next video. So the other inequality will be by the mass distribution principle. So if you want to have a look at that, there's a book by Kenneth Falconer about fractal geometry, and yeah, you can have a look at that, or I'll show you also a little bit in the next video. So that's it. Thanks for watching and have a good day. Bye.